Okay, I want you to try a little thought experiment with me. It's a bit mind-bending, but just go with it for a second.
All right, I'm with you.
Imagine you could just step outside of the universe, pop out of reality, float in the void, and just look at the whole thing.
The God's eye view. Okay,
Yeah.
what am I seeing?
Well, that's the thing. You'd expect to see, chaos, right? Galaxies spinning, stars exploding, all this movement.
Of course, constant change. Motion is what defines existence, really. If nothing's moving, then nothing is happening.
Well, according to the deep dive we're getting into today, you'd be wrong. If a growing number of physicists are right, you wouldn't see any movement at all. You'd see a static, frozen object, like a painting, not a movie.
Which means that time itself, the thing that governs, well, everything in our lives, is basically an illusion.
Exactly. And look, this isn't some dusty philosophy text. This is the deep dive. And today we are unpacking a really fascinating article from Cult. It's called "The Race of These Scientists to Prove That Time is an Illusion."
Yeah, and this is a serious active race in physics. We're talking about ideas from the early 80s all the way up to lab experiments being run, right now in 2024.
The stakes are just unbelievably high. It's about trying to reconcile the two biggest theories in all of physics.
And if they're right, our entire perception of reality, the flow of one moment to the next, is just a trick of perspective.
So here's our mission today. We are going to explain why quantum mechanics and relativity are in a fight over the definition of time. Then we'll unpack this idea called the Page-Wooders mechanism, which is the theory of the frozen universe.
And finally, we'll get into how black holes might actually be the clocks that make this whole illusion work.
It's a heavy one for sure.
But it's also maybe one of the most fundamental shifts in our understanding of the cosmos.
It is. So I invite you to just, set your watch aside for a moment, because if these scientists are onto something, it's not measuring what you think it is.
Okay, so to get why this is all happening now, we have to start with what you could call the Great Disconnect. It's sort of the big embarrassment at the heart of modern physics.
Right. Let's unpack that. We've got two theories that, on their own, work perfectly. I mean, we built the entire modern world on them.
We did. You have Einstein's general relativity, his masterpiece. It's the rule book for all the big stuff planets, galaxies, gravity.
And on the other side, you have quantum mechanics.
Which is the rule book for the very, very small stuff. Atoms, particles, the building blocks of matter.
And I'm guessing they don't play well together.
They fundamentally disagree on what time is. It's like they're written in two different languages. In Einstein's universe, time is a physical thing. It's literally woven into the fabric of reality. We call it space-time.
This is the classic flexible fabric idea, right? The bowling ball and the trampoline.
Exactly. In relativity, time is dynamic. It can stretch, it can shrink. If you're near a huge mass like a planet, time actually ticks slower for you than for someone out in space. Time is a player in the game. It bends, it warps.
So in relativity, time is a core ingredient. It's part of the putty. What about the quantum world?
In quantum mechanics, time is, well, it's just a number. It's the T in the equations. So like a clock on the wall, ticking away at a perfectly steady rate, completely indifferent to what the particles are doing.
So it's external. It's not part of the game at all. It's just the scoreboard?
Precisely. The theory of the big says time is flexible and physical. The theory of the small says it's rigid and external. And this is a total nightmare for physicists.
Because the universe is made of both big and small things.
Right. And when you try to describe something where both theories have to apply, like the Big Bang, which was both incredibly tiny and incredibly massive, the equations they break. They spit out nonsense.
Because they can't agree on what time is doing.
Exactly. The problem of time has been the biggest wall in physics for 100 years. And then, in 1983, two physicists decided to just take a sledgehammer to it.
Enter Don Page and William Waiters.
Right. They tried something really radical. They took the main equation of quantum mechanics, the Schrödinger equation, and they decided to apply it to the entire universe at once.
Which, you're not supposed to do that, are you? You're meant to look at a particle inside the universe, not the whole container.
Correct. But they said, let's just treat the whole thing as one giant quantum system. And when the math settled, something bizarre happened.
What?
The variable for time, T, it just dropped out. It vanished from the equation.
It canceled itself out.
Gone. The math suggested that from a total universal perspective, the universe doesn't evolve. It doesn't change. It's a single, static, frozen state.
So this is the Page-Wooders mechanism.
That's it. They propose the universe is a timeless catalog. I like to think of it like a giant block of amber. Inside that amber, you have every possible event. The dinosaurs, your birth, the end of the sun, all existing at once, totally frozen.
Okay, hold on. I have to stop you because I am definitely experiencing change right now. My coffee is getting colder.
Yeah.
If the universe is a block of amber, why does it feel like a movie to me?
And that is the absolute crux of their idea. It's a quantum trick of perspective. It all comes down to entanglement.
Entanglement, the spooky action at a distance thing.
That's one way to put it. But really, entanglement is about correlations. It means you can't describe the state of one thing without also describing the state of another. Page and Wooders said, yes, the whole universe is static, but the parts inside it are all entangled with each other.
So we feel time because we're inside the block, comparing ourselves to the other things in the block.
Exactly. You are entangled with your coffee cup. You compare your state to its state. And that comparison, that relationship, creates the illusion of a sequence, of a flow.
I think I need an analogy. This is getting pretty abstract.
Okay, there's a great one from a science communicator, Zach Savitsky. He says to imagine the universe as a manuscript.
A book, okay? I like books.
A finished book, sitting on a shelf. The story's already written, the ink is dry. That physical book is the timeless, static universe.
Yeah.
It doesn't change.
Got it. The universe is the book.
Right. Now, think of a clock not as the story, but as the page numbers.
The page numbers, okay.
The numbers create an order. Page 10 comes after page 9. If you're a character inside the story, you experience the plot unfolding page by page. You feel the forward momentum.
But if I'm the one holding the book...
If you're holding the book, you can see that page 1, page 50, and the final page all exist at the exact same time. They're just pieces of paper stacked together.
So time is just the indexing system that lets us read the story. It's not the story itself.
That's the page Wooders mechanism in a nutshell. Time is an emergent property that comes from the correlations between the parts. It's not fundamental.
You know, it also reminds me of a video game.
Oh, how so?
Well, the entire game world, every level, every character, every outcome, is already burned onto the disk. It's static. The data doesn't change.
Right, the data is a frozen wave function.
But when I put the disk in and start playing, I'm entangling myself with it. I experience the story. I feel the clock ticking down. But the disk itself is still the same static object it always was.
That's a perfect analogy. You activate a timeline by observing it from within.
Which is a cool thought experiment for 1983. But for 40 years, that's all it was, an idea you couldn't really test.
Exactly. You can't actually step outside the universe to check.
Yeah.
But this is where the story jumps forward to 2024. This is where the race really heats up. Because a researcher in Italy, Paolo Verrucchi, figured you don't need to leave the universe.
What do you do instead?
You build a tiny one in a lab.
A simulation.
Not on a computer. A real physical model. Verrucchi and her team built an actual quantum system to see if this idea works in reality.
Okay, how on earth do you build a tiny frozen universe?
You scale it way, way down. She took a quantum system to act as her universe and another tiny system, a set of little magnets, to act as the clock. Then she entangled them.
So she linked them together, one big system.
Yes. And then she looked at it from two different perspectives.
The outside view and the inside view.
Exactly. First, she acted as an external observer, looking at the combined system from the outside, not entangled with it.
And what does she see?
Nothing. The system was static, frozen. Its total energy didn't change, just like Page and Wooders predicted. From the outside, there was no time.
Wow. Okay, but then she looked from the inside.
Right. She then measured the universe part relative to the magnetic clock. She took the internal perspective, and instantly,
It came to life.
it started ticking. The system began to evolve, to change. She observed dynamics. And here's the kicker, she said, and I'm quoting, "You can derive all the equations of motion that we know work just from that change in perspective."
That is just wild. She literally turned time on and off by changing her point of view.
It's powerful evidence that time is a relational, emergent thing. It's not the stage, it's a relationship between the actors.
But that raises another question. If creating time is like reading a book or playing a game, does it cost anything? I mean, my game console gets hot. It uses electricity. Is time free?
I'm so glad you asked that, because that is the next piece of the puzzle. That's where things start getting expensive.
And for this, we're going to Vienna.
To Vienna, yes. To a physicist named Marcus Huber and his team. They started looking at the thermodynamics of all this. They asked, if time is emerging, what's the fuel?
What did they find?
They found that keeping time creates heat.
Explain that.
Huber's models showed that to have an accurate clock, to create a clear sequence of before and after, you must increase entropy.
And entropy is just disorder, right? The general messiness of the universe.
Right. We usually think entropy increases as time passes. An egg breaks, a room gets messy. But Huber is suggesting it might be the other way around. We experience the flow of time because our interactions are generating entropy.
Wait, so the act of measuring time is what creates the disorder?
Yes, there's a direct trade-off. The more accurate you want your clock to be, the more heat you have to release, the more disorder you have to create.
So turning the pages of the universal manuscript actually costs energy.
It does. And this is a huge deal because it means we can actually measure it. This takes it out of pure theory and puts it into testable experimental physics.
We can measure the heat, we can measure the cost of time.
Exactly. If they can measure the entropy produced by a tiny quantum clock, they can prove this whole mechanism is real.
That's incredible. But, we're building these tiny clocks in labs. If this is how reality works, surely nature has already built bigger ones.
Nature's timekeepers.
Yeah.
Well, Verrucci, the researcher from the Italian experiment, thinks she knows what they are.
Let me guess. Black holes.
It always comes back to black holes.
Why them, though?
Because they meet the 3 criteria for a perfect page-Wooders clock, almost. Poetically.
Okay, what's the checklist?
First, you need a ton of energy to track the dynamics of a huge system.
Check. Most energetic objects in the universe.
Second, you need to be isolated. A good clock can't be messed with by outside noise.
And nothing gets out of a black hole. It's the ultimate quiet room.
Right. But here's the third, most crucial part. The clock needs to be isolated, but it also has to be entangled with what it's measuring.
That sounds like a contradiction. How can you be separate and connected at the same time?
This goes back to Stephen Hawking in the 70s. Hawking radiation. He showed that particle pairs are created at the event horizon. One falls in, one escapes.
The particle divorce, right.
But they were born as a pair, so they remain entangled. The particle that flies off into the universe is forever linked to the one that fell into the black hole.
So the black hole is connected to us, but fundamentally walled off.
Exactly. Verrucci puts it perfectly. You can't interact with it, but at the same time, you can be entangled with it. That makes it the ultimate stable reference point.
It's like they're the page numbers for the whole galaxy.
That's a great way to think about it. They could be the anchors that give our corner of the universe its sense of now.
So where does this race go from here? What's the next step?
Schubler's group in Vienna is designing the next wave of experiments. They want to use what they call clouds of atoms, much larger quantum systems, to test this with more precision.
And what are they looking for?
They want to answer the big one. They want to know about the texture of time.
The texture, like is it smooth or chunky?
Pretty much, yeah. Does time flow like a continuous river? Or does it advance in tiny, discrete jumps, like the individual frames of a film?
The pixels of time.
Exactly. If time is just us reading the manuscript, it's possible there are individual pages. We could be living in a stop-motion movie, and the frames just go by too fast for us to see the gaps.
Okay, that is a lot. Let's try and recap this before our listeners need to pull over.
Good idea.
Okay, step 1. Physics has a time problem. Relativity says it's physical. Quantum mechanics says it's not. They don't work together.
Step 2. Page and Wooders propose a wild solution in '83. The universe is a single frozen block containing all of history at once.
Step 3. What we feel as the flow of time is just a trick of perspective. It's us, inside the block, comparing one part to another through quantum entanglement. We're reading the page numbers.
Step 4. And reading those pages has a cost. It generates heat and disorder entropy. We're now building experiments to measure that cost.
And finally, black holes might be nature's perfect clocks, and the next big question is whether reality is a smooth movie or a series of tiny static frames.
That's the whole mind-bending story. It really does change how you see things.
It does. We spend our lives so worried about time, running out of it, saving it, wasting it.
And yet, from this point of view, it's all already there. The book's already written.
There's something weirdly comforting about that. It means now isn't this fleeting thing we're always losing. It's just the page we happen to be reading. So before we sign off, I just want to leave you with one final thought to mull over. We talked about that movie film idea, that time might be a series of static frames, if that's true. If reality is just a succession of frozen moments, what's in the gaps? What exists in the black space between the frames of the movie? And if the manuscript is already printed, if the ink is dry, can we ever really change the page?
Now, that is a question physics definitely doesn't have an answer for.
Yet. Something to think about. Thanks for diving deep with us today.
See you next time.
See you in the next deep dive.